John here, messing around with this S100 rig that has a California Computer Systems S100 bus floppy disk controller in it, connected to a 3.5-inch floppy. Big thanks to everybody that supports my channel. I really appreciate it. Like or subscribers, please. If you enjoy these videos, subscribe or comment or something. It helps the YouTube algorithm. Special shout out to the VIPs listed here. Have gone above and beyond the duty. Thank you very much. So far what we've done is we've got the basic sanity checks of the 3.5-inch floppy interface to work. We are able to read and write sectors to some degree using the MOS ROM monitor that comes with the CCS board that I am using, which is a 2422. The code you see in the video today will be posted up on this GitHub repo here. If you're new to my channel, what's happening here is if you go in here and you click on tags, you'll see a date code in here that matches the little date code at the beginning and at the very end of the video on YouTube, so you can find the exact version of the exact code that you saw me present in the video. I do this as a courtesy to you and me so that we can tell what changes over the course of time, so you don't have a complete disorientation if you see a video that's, 6 months old and maybe I've renamed a file or edited something in here and it doesn't look the same anymore. I personally find that offensive beyond comprehension. So anyway, as a courtesy to you, that's what that's all about. That's why there's a date code at the bottom of every one of my videos. So let's take a quick look-see here. If you don't already know, remember that floppy disks, 3.5s look like this. A couple of holes on the bottom. The hole over here has to do with indicating whether the disk is a high-density disk or a regular double-density disk. And that means that if it's got an extra hole over here, it's a 1.4 meg. If this hole's not there and it's plastered over, it's a 720K. The guy over here with a little switcher on it is your write protect hole. You can flip this thing back and forth. If it's covered up like it is in here, you can write on the disk. If you open it up and it's see-through, like the one over here, you then cannot write onto the disk. And this is a nice improvement over the 8-inch and the 5.25, because you actually had to get a piece of tape because they were actually a notch in the side like this. So this was a nice enhancement. As they show the inside of the disc, there's a lubricated disc to cut the friction down on the magnetic surface. They don't wipe all of the oxide off of this thing, just so it spins nice. It's got like a reinforced metal ring. And I mean, this is a really nice design, the 3.5, way nicer than the 5.25 or the 8-inch door that closes up and covers up access to the. These were, better off for people. You can throw them in your backpack or something like that, and it's somewhat rigid, so you don't fold it and crinkle it up. It's a nice design. The reason we're here today is because I wanted you to see this. See these concentric rings? Those are technically called cylinders. A lot of people confuse them by calling them tracks. In fact, it might even do that here. Blah, 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 blah. Disk, yada, yada, yada. It doesn't use either word. So technically, these are cylinders, because if you have more than one track at the same radius from the center of these of the disk, they stack up, vertically into your, into the screen that you're looking at here. And therefore, one cylinder may have multiple tracks. In this case, it has a front side and a back side, or side 0 and side 1. So there's 2 tracks to every cylinder on a 3.5-inch floppy, or at least the ones that are the most overwhelmingly common ones that are pictured here. Okay, they're double-sided, in other words. Each track is broken up into a number of sectors. They don't have to be radially aligned as they're drawn here. It turns out today you'll see why they generally are, but they certainly don't have to be, because every track could, in theory, be recorded in different, sector sizes and encoding formats or whatever. No one cares, okay? So drawing it like this is, again, the most overwhelming common case, but do not get married to the fact that because most people use it this way means everybody does. No, that's not true, okay? So how does this whole thing work? There's a notch here that causes this disk to lock into the mechanism in the drive. This thingy here keys the media, all right? So that when you put it in a drive, it gets, kind of latched in the same rotational orientation on any drive, so that the index marker that's not on the disk itself, I mean, you could argue that the notch here this hole is the index marker, but the disk itself, the drive, I should say itself, has a sensor in the drive with a marker in the drive to determine where the beginning of each one of these cylinders starts, okay? And that's called the index. And there's a special signal that comes out of a floppy drive that says the index pulse is now occurring, which means that the rotational angle of the medium is at a very specific, well-known orientation right now that represents the beginning of a cylinder. Okay, so with that in mind, that imagery in mind, now this is kind of the unraveled entire circular view of all the sectors on one track of multiple tracks that make up a cylinder. So what you see here is in time order. This is the 1790 series data sheet here for the controller that we're going to be playing with on this card. When the disc rotates, there's a pulse that says this is where the beginning of the track is. And that pulse, the index pulse, as they say, is the thing that's tied back to this notch. So as the disc goes around and around and around, in theory, every track starts at the exact same place as the disc rotates. So there is a point where usually all the tracks will be starting in the same place. It turns out that when we're using a soft sector disk controller, it's not so much necessary for that to happen. It kind of really doesn't matter by the end. This is still used and very useful to use in the 99.99999% of the cases, because the controller itself uses this to say, if I've asked it to read a sector and it has seen several index pulses pass, like 5, and it has not yet found the sector it's looking for, it will abort the command and terminate. So this is still used. This is like, the L-bolt handler in BSD Unix. Go ahead and Google it. Anyway, the track format. This is what we want to look at today. We want to see, there is a special command that says read the entire track all in one go. Dump the whole thing into memory, and I want to look and see what's in there. And why do I want to look what's in there? Well, as you can see, there's a lot more than just a couple of sectors located on this thing. This is the best scan I can find. Sorry for the font. I couldn't find my hard copy, or I would have scanned it in myself. At some point, maybe I'll do that. I don't know. It's yet another project I got to deal with. So it says index address mark. So what happens is the disk goes around and around and around. Normally, in the vast majority of all cases, when you format a floppy disk, the index pulse goes off, and you say, okay, I will now, in one go, write all of a blank track down there and create all these things in the order that I want them and of the size that I want them. For a standard PC floppy running at 720K, which we're going to look at today, there's a fairly common format that is used, some of which is required by the disk controller itself, and some of the stuff is sort of optional, like how big you want the individual sector data blocks to be and so on. So let's have a look, see at what's in here. You get this pulse, and when you're recording the disk, what you do is when you're formatting the disk, I should say, you wait for a pulse to go by, and then you turn on the right current in the drive, and you spew this whole thing out in one go, and it tells you write so many bytes of this value, then put this index address mark on the disk, then have a post index, 32 bytes or whatever it is, 54 bytes. So it says FM and MFM. Double density is MFM. Single density is FM. So you'll see here, if we're recording in single density mode, we will have half as many bytes as we do when we're in double density mode. It's as simple as that. We'll talk more about the actual encoding of all the magnetic flux and all that other stuff some other time. If you want, go ahead and let me know in the comments below if you'd be interested in hearing more about that from my perspective anyway. So, okay, so what you have are these gaps, and you have these address marks, okay? Eventually, you get to the point where it says, I'm going to have a record ID. And there's many of these. There's one for each data field, okay? Each sector, okay? So what you have, along with the index address mark, there's only one of these per track. I should have pointed that out. This is the thing that tells the controller, hey, you're at the beginning of an entire track. Now you might say, why the heck do I need that when I got the index pulse? Well, we'll talk more about this if we get into the details of all the timing and all the individual pulses, what MFM really is and how it works and all that fun stuff. The short of it is the pulses from the magnetic flux transitions on the disk surface have to be synchronized to the disk controller. It's really a fancy UART. In the simplest of terms, that's what's going on here, okay? So on the one hand, it says the track begins here. On the other hand, I need to know kind of the equivalent of a start bit and a parity bit and all this other fun stuff like you'd see in a regular old UART, but this is a really fancy one, okay? So what we got to do is say, what's going to happen in what order on this disk surface. So what you have is I'm the beginning of the track, then you have I'm the beginning of a sector. That's what this is really for. And what's in there is a special thing. This is kind of like a start bit in the simplest of terms, so that it can synchronize itself and read this thing. It'll see a track number, side number, a sector number, and a sector length code. And then these are validated by CRCs. Because if you get a bit error at this level, you could have a huge problem. You need to really know, is this really the sector that I think I'm going to be reading or writing or whatever? You don't want to accidentally do the wrong one. So this is 10 tons of security to have a 2-byte CRC at a 1, 2, 3, 4, 5 byte field. In fact, the CRC doesn't even include, I don't believe, the address mark. Then you have these gaps, and you'll see each one of these is shown, and rather than exploding them all out and all bunched together, this gap 2 here repeats. So after the actual data field here, the sector itself has a gap before it. There's the sector. There's a gap after it. Then you get to the ID of record number 2, which is the same as this, but it's for the next one. So this gap 2 here, in other words, is the same as this one here, but it's for the following sector. So if we look down here, and this is the key. This is absolutely key. You need to understand this before we look at what happens if we try to read this whole thing. All right? So look what happens. You've got this gap. You have an ID of some kind, or I should say an address mark of some time, followed by data. And you got a gap. And you got some data. Gap, ID, gap, data, gap, ID. What are the gaps for? Let's look and see. Well, you've got data here. Or I shouldn't say data, because data refers to a sector data. The gap, the bytes in a gap, exist for no other reason than to make sure that when you replace the data in this data field, this sector, I want to be able to rewrite it in the future. Okay? And think about what that means. The thing's spinning around, you're going, okay, when the disk rotates and the head in the drive wanders into this data sector area, it has to turn on, record a bunch of bytes, and then turn back off again. And optimally, you'd like it to do so in such a way that if the recording of the pulses goes on and then goes back off, around this data value in this sector, it can glitch all this surrounding data for all kinds of reasons. What if the disk motor is not going the exact perfect right velocity? Well, it might mean that this is physically going to use a little more space or maybe a little bit less space than it should, Or, maybe it was formatted with it a little bit longer or a little bit shorter. Because, again, the variation of the drive speed or the rate of the pulses coming out of your disk controller as a result of your crystal and all this other crap that could be running ever so slightly different. That's what the gaps are for. It gives you a time to say, turn on here. Right? Gate, turn on for update of the next data field happens here. Then there's a bunch of bytes. And then there's a data address mark. We'll see that in a minute. That's actually this over here. And then the data goes out. Then in this in this section here is where the data goes. I shouldn't use the word gap unless I mean a gap, right? Okay, now here's the data field exploded here. So you got this data or deleted data address mark. So this is our third kind of address mark. You got the track address mark, or I should say the index, right? Then you got this next address mark that goes along with the data that describes the following sector, okay? Then you've got another address mark that says I'm the beginning of the data area, followed by a CRC. And these are basically recorded. Look at this. Really much the same thing. This is a fixed size. This is variable size, this is tiny, and this is hopefully much bigger than 4 or 5 bytes, okay? And again, the CRC to make sure that when you get it back in, at least that it looks like it's okay. After that is done, right, after you've finished getting the data part, during the recording process of replacing the data in this sector, it has to be able to turn off the write gate and do it in such a way and during a time where, like I said, if the disk rotation isn't perfect, it may miss. It can't really be expected to turn on and off at the exact right point in time for the specific bit of all the bits in a row that represents the entire track around an entire circle. It's just not going to happen. It would be stupid to even try. So even in day one in the 1960s, these formats that represent what IBM coughed up when they first said, let's use an 8-inch floppy drive for something, they knew this was going to happen. So that's what these are all about. These gaps give you a time to say, shoot here and hope you get pretty close. Because it's okay to be wrong. Specifically was designed to tolerate this. These address marks, as we'll be about to see here, exist solely to resynchronize the clock like the start bit does on a regular UART. Okay? And when you shut it off, you could miss the mark as well. Well, what do you got there? Well, they give you plenty of extra bytes here if you run a little bit late or you end a little bit early or whatever you're going to do. It's okay, because by the time you get over to here, there's been enough data that's been flowing by for the thing to resynchronize itself, all right? To some degree. Maybe we'll have to do an entire video talking about synchronization and all the clocks and all that other fun stuff. If you're interested, again, let me know in the comments below. Because getting the controller resynchronized to read the exact bits at the right time is not that's 99% of the problem with these disk controllers. Okay, so anyway, you got this over and over and over that happens on a track. Now the concern about turning on and off the write gate and replacing the data in a sector is only something that you even have to care about if you are going to replace the data on a disk. You know, if you record it once and you never record it again, and in theory it's like a read-only disk or something like that, well, then maybe this won't be of any consequence. You know, it'll just, you lay it all out once and don't worry about it. Turns out that never happens. You need to be able to replace these sectors in here. My point is that in theory, you could record it once and never have these problems and have it synchronized perfectly the whole time, because it won't then be used to replace a sector with one that's the wrong size and cause all the bits to get screwed up, okay? I'm just saying. All right, so the track then eventually runs all the way around the entire disk and eventually ends with the next, the arrival of the next index pulse, okay? Now, this goes on to say, look, if you're going to record it in System34 format, which is MFM, which is double density, this is an example of if your sectors have 256 bytes in them. As we're about to see and be reminded of, the IBM PC used 512 bytes per sector. which is not discussed too much in this manual, other than to say a non-IBM format, which is ironic because the IBM PC uses this format right here, the 512. But remember, this manual was printed, I don't, the dates aren't on these pages here. This is from 1980. The IBM PC came out in 1981, and the 3.5-inch floppy was another 4 or 5 years later. So at the time, 512 bytes per sector was not on IBM's horizon. Okay, now, what they show you here is another view of the same thing we just looked at above. Here's an entire track. In terms of what are the byte values, remember, just like a regular UART, you're sending 1 bit at a time, which is what we're doing here, but you gather them into bytes and you really kind of process them 1 byte at a time once you've, deblocked and extracted each character. So on a floppy disk, once that process is done, it looks like this. Here's so many bytes whose value is this, so many bytes whose value is this, so many bytes of this, and so on. So when you format a disk, when it's a virgin disk, or maybe it's got stuff on it already and you're going to just wipe the whole thing clean, you can use something called the WriteTrack command. Today we're going to talk about ReadTrack before we do a WriteTrack, because there's something you want to see before we screw up the disk. These commands allow us to just dump this entire thing out in its entirety. So if I was using a WriteTrack, and that's what you use to format the floppy, okay, I would say write all these in this order, followed by, and there's an asterisk in here, if you have 256 bytes per sector, and we're recording it on an 8-inch floppy, by the way, which is this manual is entirely based on what you would do if you were going to record or read on an 8-inch floppy, okay, which, of course, we're not doing. But in all these, convert these as appropriate, and that is comparable to what we're doing. Okay, we just got to be careful about how many sectors and how big they are and stuff like that. So it says right bracketed field 26 times. It's because on an 8-inch floppy running in double density mode with 256 bytes per sector, there is 26 sectors per track. Okay, so on our case, we can only write like 9. So adjust accordingly. All right, so what are we doing here? You got 80 of these, 12 of those, and so on. Well, if you scroll up here and you look really closely, you'll see there's a bunch of stuff here. There's 3 bytes of C2 in MFM only. All right, again, keep our bearings here. Remember, this is MFM. This is this format. If I scroll up from here in this particular manual, you see another one of these tables. This is for single density. This is FM format. You'll see the byte values are a little bit different in FM format, so don't get disoriented here. I'm looking at the one down here, okay? Okay, and it says, you can, if you want, write different values in certain cases if you really want to. Notice this PLL lockup time. This is going to be a big deal if you go Googling around and say, I want to understand what's going on in more detail. This is everything. It stands for phase lock loop. This is the thing that causes the controller to synchronize itself to the arrival of the bits that are flowing off the disk surface, okay? And that rate of bit arrival is going to have glitches when you turn on and off the write gate. So what we'll see when we do a read track, and it's the whole reason we just walked through all this, you're going to see a lot of crap coming in here around this, followed by stuff that makes sense for the actual data. And then when the write gate goes off, it'll glitch and you'll see a lot of crap again until it resynchronizes again. All right, so from the bird's eye view, you'll see a bunch of garbage, you'll see the address mark, and you'll say, oh, I can now read, and it's fine. And then you're going to get up to this gap over here where right before the data sector starts, and there will be a glitch and be a whole bunch of garbage before the data sector, followed by an address mark, and these things have special synchronization bit patterns in them. And then you'll see data you recognize. Garbage, good. Garbage, good. All the way around the whole disk, okay? So it'll sort of look like this, but it won't be perfect, okay? When you first start reading the track at the index pulse, these, I don't think I've ever seen them come out right. But in theory, they could. And if you look at the actual bit patterns, just like on a UART, if you're running at full speed and you are not synchronized to find the right start bits, and each byte that's encoded is like 10101010, then it's hard for the UART to figure out the difference between a 0 in any given bit in a character and the start bit. It's at the beginning of a character, and it'll return crap until it kind of has a period of time where you've just got a whole lot of ones in the case of a UART in a row, so that it can resynchronize to the leading start bit, which is a 0 when it's encoded at the beginning of a character. Well, the same thing happens on a floppy disk, okay? So this is your, I don't know what the heck I'm doing, and then you get to the FC here, this index mark. If you read all this, you read all the user application notes and user guides. What's happening is when we're using the WriteTrack command, I'm not just writing bytes out onto the disk surface whose values are what I send a controller. Yes, to some degree that is true. I am doing that unless I send it a byte value that's greater than like F0. These FC, FE, F7, FB, see all the ones that say address mark, and then the CRC. These are special commands that the disk controller is looking for during a WriteTrack command. I know we're going to do a ReadTrack today, but with these, we will see these. These address marks, when they synchronize correctly, we'll see the FE followed by the data we recognize. Before the FE, a lot of this could be garbage. Same with the FC. We'll see that. What comes before it? Well, technically it should be this, but if the thing's not synchronized, it could look like crap. Followed by perfectly legible 4 E's, okay? So think about that, right? So where's the gap, right? This gap here has, if we zoom way in, I wish they would have labeled this a little clearer. You got, 22 and 12 in MFM mode down here. So down here, we have to infer that takes case. There's the 12 and the, I'm sorry. There's the 22 and the 12 right here at the beginning where the write gate goes on before the data address mark and the data sector itself, okay? So what'll happen is there might be some garbage in when we read it in here, and then it'll get then resynchronized when we get to the data address mark, because the write gate goes on between, I believe, with the 4E and the zeros before the 12 zeros, right? Is that what we got in here? We see there's the 22 and the 12 and then 3. Well, that's this right over here. Where is it? The 22, 12, and the 3 right there, okay? So the write gate turns on after these 4 E's and before the zeros. So I submit that when the sector, or when the track is written and formatted, all this up here you never replace later on. So there's no, write gate turns on here kind of stuff. You don't replace the ID address mark ever. It only is one time written during formatting, okay? You do replace these. So what happens is you should be able to read all this fine. Then when the write gate goes on, it could wreck, some of the 4 E's if it goes on too soon, or it'll come on in the middle of the 0. Somewhere in here it'll be crap until we get to this F5 and the FB down here. This is for sure when it resynchronizes itself, okay? Then the data, then you'll see some CRCs, and the write gate will turn back off and wreck half of these 4 E's until we get to the next sector, all right? So, all right, keeping all that in mind now. Okay, without that, you're not going to be able to interpret what we get out of this, because half the time it's going to be spewing garbage, and we need to know why. Otherwise, we'll think we're making a mistake. All right, so you've seen a lot of this before. This is the head stepper program, but what I've done is I've added what did I do? I added a ReadTrack command and a dump it command in here. So we can hit D, and it will read a track, and I've got some hacks in the code so we can read part of a track or all of the track, because you're going to see we got an issue that we have to deal with and analyze here. Okay, so otherwise the rest of the stuff up there is the same. Here's the dump it routine. I've just hard coded this buffer, which is stupid of me. I should have put this up here and used it for everybody like this instead of having it hard coded all over the place, so that if I move it, then everybody will agree on where it is. Okay, so what are we doing here? 23, I don't know what the heck that is. Oh, that must be the ending. Yeah, I'm going to just say, I make a call into the MOS boot ROM here in the middle of the hex dump routine. I didn't feel like writing my own. That's what this is. You can look at the source listing and find that if you want. I explained that in an earlier video how to do that. Then we end the last line. This doesn't put a carriage return at the end of the dump. And then we tail call the pertwa and we get out. So that's how we dump it out for the D command. The ReadTrack, which we just played with a little bit. How does this thing work? Well, the short of it is, okay, back to the manual here. The commands are documented in here. And you see, last time, in fact, we just saw it scroll by. We were looking at the restore, go back to track 0 in the last video in this playlist here. There we go. So we have this command, all these commands. One of them we can do is read the whole track, which is going to be an E followed by something with an E bit there. That big E, I think, is described, I don't know, somewhere. If you set it to a 1, what it does, there you go, it puts a delay in there. So sometimes when you're writing commands out to the floppy, you want to give it time for the head to settle. Is that you just selected the drive, the head could be bouncing around a little bit, and you might want to say wait 15 milliseconds or not, or whatever. So I think in this version, I usually see an E, what is that? It's an E4 or an E0, depending on whether or not I added a delay, and I think I put an E4, E2. Hello. Wow. That is a mistake. Wow, single D to, oh, that's not the command. That's control register 1 in the disk controller card. It's just a coincidence that it looks so similar. So control register 1, that's status register 1, that's this guy here. So I'm going to set it to an E2 or an A2 for single density versus double density, okay? So that just means that these two values differ in this bit right here. So we want auto wait on and motor on. And this bit here, I already explained that they decided to label this thing backwards just to piss me off personally. The world's out to get me, I swear to God. To enable disk B, which is what you get if you use a straight through cable on a PC floppy the way I have it wired. We talked about that before as well. So you either want all 3 of these bits on for double density, or you want this bit 1, 0, 1, followed by 0, 0, 0, and a 1 down here. Meaning it has to do with controlling the clock speed of the controller to let it know whether it's going to go at double the rate or not. And in this normally what that means is it's a 5 1/4 inch disc versus an 8 inch disc, because the only real difference between the two is that it doubles the rate of the bits flowing onto the disc, which is exactly the same relationship between a 720K double density disc and a high density disc in the 3 1/2 inch format. So when we get to the high density, we'll turn this bit on and see if we can wake it up and make it read and write to a 1.44 megabyte floppy disk, which I've yet to try, but that'll be another video, okay? So, all right, so that's what I'm doing. I'm telling the controller card to run at the right clock speed and stuff for what it thinks is a 5 1/4 inch disc with the right density and all that. Auto wait here is an interesting thing, and I don't have the equipment to show how cool this really is, but the bottom line is that when I set that bit, it says, okay, waits are disabled after reset, blah, 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 blah. You're going to have to read the narrative and go through the entire schematic to understand what really is going on in here, but the short of it is that this, if you set this bit what'll happen is that the floppy disk controller card, the 2422, will automatically assert an infinite number of wait states back to the CPU every time it reads from the controller. And the reason we want to do this is because what we're going to do is we're going to send a command into the controller, and then we're going to say, I want to read a whole track. And I'm going to say, I'm going to set this bit, which you just saw me do because that's what the most significant bit is in this thing when we write it out. And that way, when I get to the part where I say, okay, I want to read the data register in the controller using an INIR at the maximum spin rate I can in the CPU. Well, what that's going to do is it'll tell the card to stop the CPU with wait states until the controller has a byte that is ready to be read from the floppy disk. Now, if you don't use a hardware assist mechanism along these lines, you can't write a loop that will iterate fast enough to keep up with the data that comes off a double density 8-inch floppy, which is the same thing as a 1.44 megabyte 3.5. You just can't do it. It takes too long to ask, to do this down here is what you'd have to do. You'd have to read the status port. You'd have to ask if the bit is set that represents the "Are you ready now?" And you'd have to spin on that. And when you're done with that and it is ready, you then have to come back up to this loop here. You just can't, it can't be done because the clocks are too fast. So their solution, okay, I'll withdraw that. If you run your CPU at like 20 megahertz, it could be done. In the era when this board was in use with 2 megahertz and 4 megahertz with Z80s, it couldn't be done with that hardware, which is what we had to work with. So what they did is they created this hardware assist thing. Now, you have to be very careful and not turn this on when you don't want to use it because it'll generate wait states and seize up your whole thing, and it'll be stuck in wait states forever. Okay, so if you're going to play with this, be careful. So I'm going to set the auto wait. I'm going to select side 0 by writing out the control register 2. Now, there are other versions of the controller that allow you to do this with the controller itself. This controller does not have a bit in its, implementation and a pin that comes out to send the side select signal out to the floppy to tell it which head to use. So they just implemented it with a latch and just routed the wire from a latch out to the floppy drive. And I got to tell it, you want the top or the bottom of the floppy, side 1, side 0. Okay, so that's what I got to do here. That's what I'm doing. I'm putting a 4-0 out this port, which sets this to a 1, which if you read the documentation, 1 selects 0 and 0 selects 1 just to keep us on our toes. This, I don't know what the heck, this set to position this, it disables the boots, this thing has to do with whether I'm going to use the automatic bootstrap mode in the MOS monitor and all that crap. We're not going to do fast seek, we're not playing with this, so I only want this guy here on to select side 0 so we can recognize the data because we've already read side 0 sectors using MOS. Now we can do the same thing and read, side 0 with a ReadTrack and see if we can recognize what the heck's going on. So that's why I chose to do this. Now, I also wanted to zero out the buffer that I'm going to read into in advance. And if you look, I say RT buff plus 100. I'll leave the +1 -1 garbage for the viewer. That's because we have to initialize this and leapfrog the copy to pad out this thing with zeros. I talked about that on my channel before. It's a very common thing to do with Z80. If you don't follow it, think about it for a few minutes or Google it. This will be very common idiom that you'll find on the internet. So what do I got? Load BC with D data and HL with RT buff. This is the target. The comments are true. This is where to put the data that's being read in. These are setting up the INIR instruction down here, okay? BC holds the byte count and the port to read from when it's spinning in here, okay? So the port is this D data value. I'm reading from line like 31 or something like that. These equates are up here. 33, okay? This is the data port coming out of the controller. That's where the data is going to arrive. So I'm going to read it out of there, and I'm going to wait until until the data arrives with the auto wait mode. It'll stall until there's a data byte ready. When it is, this thing will read it, and it'll put it in memory at RT-buff. It'll add 1 to HL so that it just continues to march through memory as it reads. The B register is the total number of bytes you want to read from the port, and by loading the register pair like this, it ends up putting 0 into the B register. 0 means 256. Nobody would use an instruction to read 0 bytes, so they were able to then make it a nice power of 2, where 0 represents 256, instead of having it only go from 1 to 255, okay? So I set this up. What am I doing? I said D, auto wait mode is terminated when this will read this many, okay. This is because 256 is not enough bytes to read a whole track. I need several K. And up here there's a pound define. I had it set to 8. I currently have it set to 2. We'll see why I did that in a minute. Let's put it back to 8. It turns out the entire track around a 720K disk is about 6.5K. If I read in 8, I'll certainly get enough data to read the whole track, okay? So it's 8K starting at 2,000 in hex, which means it'll go all the way up to 4,000 in hex, because 4K is 1,000 in hex. All right, so this thing here is how many 256 byte passes with this instruction do I want to do? So I'm going to, right now, I just set it to 8K, so I'm going to read a quarter K per iteration, so it's going to end up, this will be 32 times it wants to do this. Double density read track command. So this is what I was talking about earlier. The actual read track command is E4, not E2, and the 4 is that 15 millisecond delay bit, and E means read track. I throw that out the command port, and then I immediately start running my INIR, which will stall every time it reads from the input port, because, as I said earlier, the auto wait bit was set when we wrote out control register 1 right there, okay? So this will stall, a byte will be ready, it'll say thank you very much, it'll take it, put it in memory, go around internally in the INIR, it'll read 256 bytes. When it's done with that, it will fall down here, and because I loaded D with 32, it'll decrement it, it will not be 0, and it'll immediately go back up and keep reading. This takes a little while to do this. I wonder if I should have just used a jump command, because a relative jump is slower when the jump is actually taken and faster when it is not taken. So this is optimizing itself backwards. Let me go ahead and make this suck a little bit less than it does now. We'll do the same thing here, because as we'll see, that is a similar kind of situation. This should run faster. And if we ask a random AI, it'll say there's trade-offs, blah, 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 blah. This thing says, if it's true, you take the jump, it takes 12 T-states. A jump only takes 10 when it's true, 10 when it's false. The relative jump is faster when it's false, so I've optimized this code backwards. This may help a problem that I've been having that I suspect it will not correct it yet, but let's have a look, see at what's going on in here. In any event, the bottom line is we're going to get 200 up, we're going to get 256 reads per loop here, and then we're going to do that 32 times in here. And when that's done, it'll fall down here, and when it gets to this point, I'm going to read the status from the controller and the DStat1 port from the card. DStat1 is this guy here, which lets me see the data request, head load, interrupt request in here, okay? And because that will make more sense a little bit later, we want to analyze what's going on. So in any event, I want to print out some status in here, and then I return from this routine to our usual loop, which will dump out more status up here and then go back in the loop. We went over the loop itself last time. So we don't need to talk about that again. All right, so if we say cat z out and we look at the mhex file, we showed you this before. I added a carriage return here to make it easier for me to just triple click this thing, come down here. Now I just turned on my box, so here we go. We can synchronize it up. This is booting the boot ROM that's on the floppy disk card, the 2422, and I say S1000 because this code loads in starting at 1000 in hex. We went over this before with a little delay in Minicom. Therefore, we can say go 10. Oops, I typed it in wrong. And you just hit a bunch of garbage and it will error out. Go 1000. It now is running my disk inspector thingy, which is the same thing we had before. If I hit space, it deselects the drive, and you can see the various status values change. Stat here is the status from the controller. The track sector values are the registers in the disk controller itself. We looked at this before, and I hit dot, and it goes one way, and I hit comma, it goes the other way. I hit R, and it'll restore the head back to the beginning. And because I forgot to select the disk, it doesn't really work. Let's try that again. If I hit S first, now the disk has been selected, and you'll notice the status changes a little bit. And then I can hit, I don't know if you can hear the clunking of the head moving or not there. And then if I hit R, it'll wing it back out to the outer side of the disk until it gets to track 0. Now, the status from the controller itself for type 1 command, we talked about this last time, moving the head in and out. It ended with a 24. So what we've got now is the head is loaded and we got a 4-bit on. So I'm on track 0 with the head loaded. That's a good thing, especially after executing the restore command. Now, if I hit the D command, it reads the entire track and the status at that time, after the track's done, I read in 8K. I'm going to hit space to shut off the disk so I don't wear all the oxide off the floppy. Otherwise, it'll run forever while I'm yakking here. So it ends with a status 4 and a status 1 of 64. Now, we finished a read track, and the status 4 is lost data. That's why I was playing around with that jump instruction. The question now is, why in the world is lost data set? You know, I stole that code right out of the MOS monitor, and I could not figure out how to read the whole track without having lost data turn on. Now, there's various reasons why that could come on that don't concern us, and then there's one obvious reason that should concern us. Most likely that we didn't keep up. So let's have a look-see. Let's ignore that for the time being, all right? So the disk is not selected, and remember I hit X to exit out of the program, which means I'm rerunning the MOS, and I hit Enter to resynchronize the UART. I can say capital D 2000, and this goes all the way up to 3 FFF, remember. Let's kill that command because it'll scroll forever. We won't be able to see anything. 2000. Let's go to 7FFF. Oops, that's too many Fs. D2000 27FF. All right, there we go. Now this should look somewhat familiar. I'm on track 0, remember? When we were playing around before, we were reading track 1, but I think I winged it out to track 0 and hacked up MOS at one point in the playlist, and this is clearly the boot sector, okay? If we want, well, we'll go ahead and read the sector, this same floppy we've been playing with the whole time. We'll go ahead and read sector on track 1, and we'll see all those, AAs or whatever we wrote out. We'll see those on the other track. In any event, this is the data that we got out of it, given the program that I wrote. You'll see all this garbage up here with the C9s. Then you see a bunch of zeros and 18. Oh, look, some 4Es. Remember when it said, here's how you format your track, and it said right out a bunch of 4Es. So let's get back to our fancy loop. There we go. This is the double density one. The 4Es we're looking at, I think, are these right there. Okay, so you're going to see that this thing should be okay. So let's go back to the beginning of our track. There we go. So it should be 4Es followed by 12 zeros, 3 F6s, which if you look, remember the F values are sometimes magical special things that get re-encoded in other ways. And other times they're just themselves. So I would not expect this to necessarily work, although you can recognize a bunch of zeros up here. These are these zeros right here. I'm sure of that. These 3 F6s, if you dig deep into all the data sheets, those F6s are special values that end up getting recorded in different. This terminal will keep scrolling and annoying me, so I'm going to go ahead and do this, and then D2 whatever 1 FFF. Get. Fine. So it doesn't keep scrolling while I'm looking at it here. All right, so in any event, these F6s are re-encoded, and I think that's why they look weird over here, okay? And then you see this FC with some 4 E's. Well, la-di-da, surprise, surprise. This is our super special bit pattern that is otherwise illegal to occur any other place on the entire disk. It's sort of like the magic start bit that can never be misunderstood. And then you've got 54 E's, and all of a sudden now we have exactly 54 E's, all right? So that would be from here to here is 16. That makes it 32. There's 48, 49, 50. Exactly. Okay, so they're following the rules. They may not always follow the rules, but so far so good. We should have then 12 zeros. 1, 2, 3, 4, 5, 6, 7, 8. That's probably 12, right? 13, 14, 15, 16 makes the whole line. So they're all accounted for. That's 12. Then we've got something over here, this 14A1A1. If you dig through all the doc, these 3 F5s will be written out as A1s in many cases. Now, I can't explain the 14, but, like I said, this is actually recorded by a PC with a completely different controller for, maybe they took some liberties there. Nonetheless, that's what that is. Those are the 3 magical mystery bytes that should have been these F6s, or rather the what am I looking at? These 3 F5s, I think, was that thing, right? So now we got an FE. Yeah, that's the FE followed by the ID address mark. So that should then be a track, side, sector. So we see track, side, and sector, okay? And now this thing says to just write an 01 in there, which I find very annoying. Thank you for being a jerk. You dig through the entire manual, and you find out, buried in a diagram somewhere, 01 means that the sector length is 256. Guess what 02 is? That's 512. That's the sector length. Here's your CRC, and then you got a bunch of 4 E's. So we're still good. All right, 22 4 E's. 16, 17, 18, 19, 20, 21, 22. Perfect. Followed by a bunch of zeros. Followed by the right gate turning on and crapping all over the place. That's what's happening here, okay? So that's why those are never going to be right. Every time we look at a sector, it's going to be followed up. So that's the 4E, the zeros here where the right gate goes on. We write a bunch of F5s and a data address mark and then a sector. So these are the F5s that go out like this. There's your data address mark. This is a real, genuine, bona fide sector on that floppy disk. Now, I've done you the favor in the GitHub repo of decoding all this stuff and the statuses and what they all mean, and the index mark, and marked them all in here for all the disks, or all the sectors of an entire track all the way around the whole thing. And I counted out all the bytes, well, most of them, certainly all the data sector bytes, and they're all accounted for in here, and yet we still have that lost data bit that gets set in the status register. Now, it may be that the lost data is caused during a gap that we don't care about, or it could be, again, in the gap we don't care about, but it could actually be, I can't figure it out. I'll run some tests and we'll have a look-see at how I reason this out in a minute. It could actually be that when we turn the right gate on and off and everything glitches like crazy, it may be that the controller spews out a couple of bytes really fast back to back in a way that we can't keep up with no matter how hard we try. And that scenario will never happen, ever, no matter what, in any scenario, if you think about it, unless we're executing the ReadTrack command. ReadTrack doesn't care because you're in control. You're writing out the bytes one at a time. There's no gaps. There's no glitches. You're creating the byte stream yourself. There's no resynchronization in gaps is what I guess I should say there, right? When you're reading a data sector, you're reading the data sector. There's no glitches in there. The write gate doesn't go on and off. So I can't prove any of this until I have a logic analyzer, and we'll talk about that some other time. Maybe we'll hook up a logic analyzer and watch the whole thing run, and we'll catch it. I don't know. Meanwhile, what we can do is this. If any of that mumbo-jumbo theory is correct, then what can happen if we read less of the track than the whole thing, and that flag is not set, what can happen is, we can kind of pick how much do I want to read before I stop reading. Now I'm using the INIR and it's reading 256 bytes at a whack. No matter how much the card provides, I'm reading a multiple of 256 no matter what. You dig through the manual about the auto wait, and when the auto wait stops, when it's generating the weights, it has to stop doing that eventually. Otherwise, we end up in a situation where there's no data, and I do a read, and the whole thing locks up. Okay, the way it stops ultimately is when the, the disk controller finishes a command. It generates an interrupt back to the CPU, or it can generate an interrupt, and it's not enabled to do so, but on the card, the interrupt signal is intercepted, and it's used to turn off that automatic wait. It's discussed in the manual in here, okay? So what happens is, when the disk controller is done sending me data, it no longer waits. At the point in time when it stops waiting, this thing runs full speed and continuously reads garbage out until the end of all the reads and the looping is done. Okay? So if we read an entire track and we look at all 8K, which we just did, by the way, let's have a look-see before I mess with the code. 2,000 to 4,000. That's the whole buffer. We watch the whole thing go by. There's a sector, there's another sector, there's a sector with some zeros, there's another sector, and so on. As we go around, this, remember, is track 0. All these C9s, there's all kinds of junk at the end of the track. So it turns out that around 36 something in here is roughly where the thing really ends. Okay? Again, if I have a logic analyzer hooked up, we can actually count and see all these bytes going and watch when things really stop happening and start when the interrupts stop happening, or rather when the wait states stop happening and the INR is spinning and all that fun stuff. We'll see that on the screen. So when that shuts down, the INIR still goes, and it just keeps reading the same junk data value that was in the data register on the controller until I stop reading, which is all the way down here at the end of 8K. All right? So that's how this thing ultimately ends if you read more than you're ever going to get, which is how this is geared. If I stop it early, on the other hand, what does that do? Think about that. So while it's running, it'll still say, here's more data, here's more data, here's more data, if I ask the status from the controller. But if I simply stop reading, what it will do is it'll get a data overrun. It will have lost data and so on. However, if in the middle of reading, I simply stop and quickly look at the status register here and the status register inside the controller, before more data arrives, which is what I hope is happening down here, right? So if it stops and it immediately comes down here, I really quickly grab these values. If I then come down here and I start printing stuff out before I read, this code down here is infinite amounts of time. But if I come out of that loop and quickly read this, I might take a peek at the state of the controller when I'm in the middle of reading a track after I've read this many bytes at the 2K mark. So let's see what we see if I do that. Take all the data here. Now, to make sure that we have a known perfect state, I'm going to hit the hard reset button on the system, resync this thing, S1000. This is a much nicer way to upload code, by the way, than burning ROMs and UV erasing. The old days, it took a half an hour per iteration to do stuff like this. Okay, let me shut the disk off before we lose all the surface oxide. Okay, so where are we at? We are status 0 and all that stuff. All right, so here we are back to the floppy controller. We haven't really done any commands yet. If I hit S to select the disk, oops. Select the drive. We see it says, what, 04 in there. That's track 0, and the head is not loaded. If we say R, okay, a couple of times. I don't know why it took so long for the head to load. Oh, that might be the delay, but that's an awful long delay. That took way more than 15 milliseconds. I can't explain that. We can look more into that later, but nonetheless, the head is loaded, and we're over track 0. Let's go to, all right, let's apples and apples. We'll hit D and read it. So in the middle of the command, I'm going to hit space to shut down, unselect the drive. We're in status 5, and status 1 is a 64. So we're in the middle of read track. Lost data and busy are on, okay? So we're already lost data, which is a little unnerving. And what does it say? Status 1, which is this thing, is a 64. So this is not set. Auto boot, head load is on, and the out of order garbage down here is what we expect. Okay, so we're fine, except the lost data bit is set. So let's go ahead and select again and hit restore. Restore command ends. Okay, and the status is 4, so it's over track 0. Let's try reading the data again. I got another 5. Let's restore it. Read the data, restore it, read the data, restore it, read the data, restore it. The reason I'm doing a restore command in the middle is to force it to do something. You can hear I'm moving the disk in and out. Forcing it to do anything at all so that I can see the status of the type 1 command, the restore command, and see that it's over track 0 and so on, and that the head is loaded. Because if you don't do something, and if the controller's hung up on this read track for some reason and stuck in here and it hasn't kind of finished a command, then it may be in a weird state. But I know the state that it's in if I can actually hear the disk head move, right? So I hit another D. No matter what I do, even if I'm only reading 4K. So let me unselect the disk, hit X, get back to the monitor. Let's go back to our program here. Let's only read, let's only do one iteration of that INIR thingy here. If I only read, well, we could do 1K or something. No, let's just read like 256. The problem with reading 256 is that it may not be enough data to actually get a whole sector. And it's certainly not going to get a whole sector. It may not even get to the beginning of a sector. How many bytes do I have to read? 256 will end at 100 in hex. So it turns out that it will get up to this first sector. This dump here in the README is on track 1 rather than track 0. And that's why you see all these AAs in here. And if you look very closely, you can see that the address mark here says track 1, sector 0, track 1, side 0, sector 1. Okay? This is the one that we wrote in an earlier video when I wrote all those AAs in there. That's why those are in there. And we're now reading track 0. And okay, so point is 256 will give us enough to recognize something that is going on. Hit the button for a hard reset. Oops, R is not the command I want to use. S1000. Paste-a-rooney. Run it. Okay, deselect it. It looks like the mode makes sense. What am I going to do? I'm going to hit select. I'm going to hit restore. And I'm going to hit D. Now we got a status 1. That is a favorable status. I remember. Let me stop the disk for there. I hit space to deselect the drive. Point is, at the end of that command, we know that we ran inir once. Lost data is not set because it's set to a 1 at that time, which means it's busy. And when it's busy, it can't do any other commands. Eventually, it prints this out. It goes up to the main routine, and then it prints out the status a second time. We don't talk to the disk controller in any way. Remember, we're just printing out. This wastes an eternity to print this out, okay? We go back up to our main loop, and we print out the status a second time. It's 07. And so in that amount of time, what happens is data request has been gone on, and we have a lost data flag, and the busy bit is set. So this does, if you waste time, will time out and say lost data, okay? So my point is, I'm pretty confident that this thing works. It's running as we expect it to, but something happens along the way where we drop a byte or something somewhere. So let's reselect the disk. Let's restore out to track 0. Hit D. Okay, restore to 0. Hit D again. So this is reproducible. I'm going to hit space to shut off the floppy. Let's edit this thingy and up this side. Oops, that's not the file I want to edit. No, my point is, as you increase this, eventually it stops working. And this roughly needs to be a multiple of 256, otherwise the math below doesn't work. So let's try and do 2 times around the horn here. What do we want to do? We want to get out of here and go back to here. I'm gonna hit a hard reset because you never really know what state you might leave some I/O port or something. And I just can't type today. S1000. Now run the program. The space bar to deselect it. Select the disk. Do a restore command. Hit the D. Look, it's working. Restore it again. Hit D. Restore. D. Restore. D. Let's go in a track. Now you'll notice I'm on track 1. Let's do a D now. We're in status 1. I'm going to hit space to deselect the disk, stop it from spinning, exit out of the program. I'm going to hit dump to 000 to I read 512 bytes. So that would be 2. Is that 7FFF? I don't know, 800 or something like that. So what we got in here, you can definitely see the A's in that thing. This 0 right here, I read the 1 extra byte on purpose because remember I zero out all the data and then I read in up to the size I asked for. So this is 512 bytes followed by 0 padding. And if you scroll back in here, we should see 2. What do we got here? On what track am I on? There's the AAAs. So inside here, we should see the address. Track 1, side 0, sector 1. All right, that's definitely the AAs we wrote in there. I don't understand why all these zeros. Uh-oh. 1F0. That's this is actually where we stopped reading the data. This is old garbage data. There's a red herring for you. So this is actually the data that it read in here. I will observe that because we stopped doing the reading in the middle of a sector, we never got to a point in time where the right gate shut off. Think about that for a minute. When the disk is spinning and we're going along and it's reading in here and it says, I want to, write a sector. Because remember, that's what we did in the past. We replaced this sector here with all the AAs in it. Okay? And let's say we ended at a point in time when we wrote this sector earlier in this playlist, and the bits ended in time and slightly glitched during this right here. What we've done here is we've read all the stuff up to and then into the middle of this first sector data field and stopped. This gap after the first data field is right here. We didn't go there. This is the most likely place where there could be a clock synchronization glitch that in theory could cause the disk controller to give me 2 bytes back to back and upset the way I'm reading, as I said earlier. It's not likely that this will cause any major problems because, these bits are, literally, they're only going at 250 K bits a second. It's pretty easy to turn on a write gate and nail the beginning of this thing. And you'll be going along fine. You could shut it off and merge perfectly as well, unless your disk drive motor is not going the perfect speed or your crystal oscillator is not the perfect speed. It could deviate from where it is and you'd have no real ability to control that. I submit that the first real clock glitch could be here, more so likely than it one ever being over there. Okay? That's why I wanted you to think this out. I'm just trying to come up with a reason why the darn thing doesn't work all the time. Point is, we didn't cover that glitch. Let's go now and read it to go 3 times 256. So it'll be 3 times through that loop at this point. And see what happens now. So this will be the first time it goes through a glitch in what they call this thing over here, gap 1. A gap 1 that follows a data sector, okay? Let me hard button. Read it in. Oops. S1. Not R, dummy. R means use the mouse command to read the floppy disk. Okay, G1000. Stop the thing. Do a restore. Ooh, command that took forever. Normally that happens when the disk times out. Something is not right. Oh, it didn't work because I forgot to hit S to select the disk. Now it will work. Let's see, the light just went on. Again, you can hear the disk move, I think, with this microphone. Now it restored properly. Okay. If I hit D, it should read in the track. Not bad. Restore, read, restore, read, restore, read, restore, read. It is working at this point with this much data. Let me stop it. I can hit P. I don't remember how much I print out from in here. Oh, it looks like I certainly did enough. It certainly prints out to the point where we got our zeros at the end of the data. I don't dump all 8K out when I do this little quick read command here. I must be back on track 0, not on track 1. Let's go back to track 1. Select the disk, track 1, hit D and read this one, because this is the one that we actually rewrote. Unselect the disk, print this one out. You can see the AAs. You can see the CRC, and the glitch would have happened over here somewhere, which is probably why these 2 bytes different value and why these 48s here don't match at all what's supposed to go in there after the, these are supposed to be 4E's, because after the CRCs are written, that's where the right gate turns off. The glitch would happen here, okay? Now, it doesn't mean that every glitch could do the kind of thing that I theorized could have happened. What we can do here is, since it does seem to be reliable, in that we can repeatedly do that. I just said select, restore, track, step back into track 1. You can see the number change right there. Hit D. It seems to be very reliably reading right now. Let me stop it. Exit out of here. Or more importantly, front button the reset thingy on there. Let's go back and raise this up a few more times. See where it starts crapping out. Now, if I do 4 of these, that's really 1K, but that's fine. Now, this is 4 times. Remember, the 256 is in my mind. This is how many times we go around this loop down here, the RD loop. Okay. Cat. And even when I type it in right, I can't type it in right because I did a lowercase s by mistake. One of these days I'll get it right on the first try. Alrighty, let's select the drive, restore it to track 0, step into track 1, hit the D command, and it didn't work. Okay, let's step it in, step it out, back to track 1, D. Look at that. It cannot read. Let's just try and read another track. Whoa, look at that. Oh, that one failed. That one worked. That one failed. Wow. Let's try to read track 1 again. That one worked. Now we're on track 0. That failed. Step in, step out. Failure. Oh, that one worked. Let's go ahead and do it to a P. Well, my point here being that the longer we run this loop, the more times it has to take the long way around and restart that INIR command, all right? Now remember, this thing was designed to run on CPM, and CPM, the sector sizes were very commonly 128 and 256. So the INIR loop that's in the main program rarely had to run more than one time. And it never would have run and read in data across one of these right gate gaps. So this could be a red herring. I don't know. There's no doubt that the longer we let the thing run and the more data we read, that statistically the more likely it is we could get behind and end up in trouble. And the main reason we get into trouble is because we end up going around this loop and taking forever to count and go back to this loop. So let's try something here. I should have done this on day 1. I'm an idiot. Let's do this, and then say else. Let's just comment out everything we've just done. Blah, 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 and then put another end if down here. So we're going to throw away this whole loop, okay? I don't really care about doing this. I'll leave that to be a task of the user. I'm already way into overtime right now. Let's do it like this. There's 256, 512. 512, right? 1K. 2K. Right? What have we got here? 1, 2, 3, 4, 5, 6, 7, 8. 8 quarters is 2K. This is then 4K. That now is 8K. We don't need to read 8K at all. We only need to really read about 7K. So let's throw away these bottom 4. We'll see it finish the whole track because I happen to know it's 6.5K. So what do we got here? If we go up here, I want to go up to and 1, 2, 3, 4. So this now will read in 1, 2, 3, 4, 5, 6K with an unwound loop, which means this will never have to waste time doing all this down here. This will restart itself as fast as it possibly can. I don't know if INIR takes longer on the last iteration or shorter. I suspect it is shorter on the last iteration because the way these instructions work, and they have to refetch themselves and update the program counter and all that. You'll have to look at the Z80 timing specs, but usually this will, I think this exits faster on the last read than it does on the rest. And in the end, this is going to be faster no matter how you slice it because we don't do the conditional branching. Let's see if this helps in any way. Hey, and we'll celebrate by me typing it incorrectly for the first time. Now I jinxed it. G1000, he says out loud to make sure he doesn't screw that one up. Okay, we unselect it. Put the disk back in the drive. There we go. Okay, select the drive. Restore to track 0. Dump the track. Wow. We got a 5. So we're already losing data. Data request is off. And it's busy. Which makes 0 sense to me. It makes me wonder if I broke the program, because I wonder if something up here, if this is, in theory, that could be used incorrectly, but I don't believe, yes, it is used incorrectly, but RT-len really only is used to clear out the buffer before it gets filled in. Right there, and then it gets used here, but we're not doing this with the unrolled loop, so it's still dying. How could it be busy here? That suggests that I didn't read enough data. What did I do wrong? Did I remember incorrectly and it's 6.5? Oh, yes. I'm an idiot. It's not 6K, it's 6.5K per track. Nonetheless, we still have the lost data bit on in there in spite of it ending early. So this one actually should end without being busy. Hard reset. Select. Restore to track 0. There we go. Restore to track 0. Hit a D. And then we end with an 04, which is lost data. Yeah, I suspect there's some more to this than meets the eye, and I'm more inclined to want to, let's get out of here, D2000 to 2, I don't know, 4000. I'm more inclined to want to get a logic analyzer in there before I do any more, or before I give a crap about this, because I suspect, here's the end of it, and trailing zeros. Okay. So I padded it all the way out to 8K, and I ended after like 7K, which must be that. Is that true? Yes. Okay. So there's all the extra noise at the end of the track and so on. I'm going to go with the right gate glitch theory for now until we get some probes on there that really look at what's going on. All right, this is just driving me nuts. In any event, that's what ReadTrack is. That's what it does. That's what the That's what these tables in here in the doc mean, and this thing here on how to format it. Next time what we'll try and do is I'll throw together a WriteTrack command that builds a table of data in memory that matches, what should be on a track based on this and the fact that we got 512 instead of 256 bytes per sector. And we'll see if we can write this out without falling behind in the data. I suspect WriteTrack will work, and I also suspect that ReadTrack will work on a freshly formatted track before we've done any updates on any data sectors, because these write gate glitches will not yet exist. So we'll see what happens there. That'll be worth doing while I wait for a logic analyzer to appear in some way to analyze what's going on with this ding-dang-dong thing. What do you think? Any other clues? Any other ideas? Let me know. I'm getting desperate with this one. Thanks for watching. I'll see you next time.